Hey, AK again, welcome back. This is video number 5 in the series called 1 Hour Matlab. In this video, we are attacking a slightly more difficult problem. We are going to numerically solve a differential equation in Matlab. If you're a bit rusty on your differential equations, don't worry. I will give you step-by-step explanations. We are again taking a practical example from biotechnology. Say you are a researcher working on an artificial eye, and say you want to match the response of your bionic eye as close as possible to the human eye. Okay, so let's look at the response of a human eye to a light stimulus. X-axis is time, and the red line is the light stimulus. That actually goes from 0 to whatever a constant value k instantaneously. So this is constant for all time. But the response of the eye, which is in yellow, it's not instantaneous. It takes a while for the eye to respond. Okay, we call the input light stimulus as u of t, which is a function of time, and the response of the eye as x of t, which is again a function of time. So this response of the eye, it can be modeled as a differential equation. What is a differential equation? Notice that the eye response is not given as an algebraic or a trigonometric equation. It is given as a differential equation. What we are saying is the time derivative of x of t, which is the eye response, is equal to some constant multiplied by the eye response itself, plus again some constant multiplied by the input light stimulus. So notice that in the differential equation, the time derivative of the variable of interest is also involved. Okay. Oh, by the way, many of the physical and biological systems, they can be modeled as differential equations. Okay. This particular equation, which is called a first order linear differential equation, and this has a neat analytical solution. Remember, this is the differential equation, and if you solve a differential equation, you get another equation. If you solve, say, an algebraic equation, say for example, a second order equation, right, quadratic equation, you can get two values as the solutions. But recall, if you solve a differential equation, you get another equation as the solution. In this case, this has a very neat analytical solution. The eye response is given as an exponential equation. So k multiplied by 1 minus e to the power minus t by tau, and the response, the x of t with respect to time, it looks like this. Let's actually fire up Matlab, and before we solve this differential equation numerically, let's plot the analytical solution. Open up 1 hour Matlab 05 iResponse.m, and this is the eye response gain, and these are the two constants that I talked about. This is just some plotting stuff, ignore this. And let me just put a breakpoint here. So we are looking at the analytical solution first, and this is just the equation that we talked about, this equation here, and I'm just implementing this in Matlab. Time vector is linspace 0, 100. This linspace is a very useful command. What I'm actually saying here is create a vector called a time vector, which has 100 elements, and it actually starts from 0 and ends at 1. It has 100 elements, and it starts at 0 and goes up. The second element is 0.01, third is 0.02, so on and so forth, until the final element is actually 1. So that's what linspace means. This is a very useful command, and this is just the implementation of the analytical solution for the differential equation. The rest of it is actually plotting stuff. So let me just plot it. This is the time vector and eye response. Unfortunately, not very many differential equations have such neat analytical solutions. In fact, many differential equations that we encounter in physical and life sciences, they don't have neat analytical solutions, and we have to use a technique called numerical integration in order to find the response, the system response. Okay, I'll explain the numerical solution to you. Again, time axis, and this is the stimulus of the system u of t. This is known, and we start at time t0. Okay, so the input to the system u of t is known, which is k, and the system response at the start of the simulation, it's actually 0. So at time 0, we know u0, which is the system input stimulus. It's known, it's k, and we know the system output response, which is the I response, which is x0. That's known, which is 0. You take these two known values and use a numerical integration formula to find the system response at x1, which is the system response at time t1. So you go to the next time step, t1. We already know the input stimulus, which is u1, and we know the system response, I response, at t1, which is x1. You use these two, this known information here, and calculate the system response at time t2, which we call as x2, and you get the drift, so on and so forth, until we are actually done with all the elements in the time vector. So this is the general idea for solving a differential equation using a numerical integration, but there are very many methods to calculate the response of the system for the next time step, given the value of the input stimulus and the system response at that time instant. So one such method is called Euler's method. By the way, there are very many different methods of numerically solving differential equations, like Range Kutta, for example, and Adam Bashworth. Those are pretty advanced methods. In this video, I will be going through Euler's method because this method is the easiest to implement and easiest to understand. If you're interested in other methods, do drop a line in the comment section, and I'll create an advanced video on that one. Okay, let's talk about Euler's method here. This is nothing but the differential equation that we're trying to solve, and in order to understand Euler's formula, we have to rewrite this differential equation in so-called standard form. We are saying the left-hand side is still the same. It's just the time derivative of the system response, d by dt of xt equals, we are writing the right-hand side as f of x of t, the system response, and u of t, which is the system input stimulus. Okay, so nothing new here. What we are saying is the right-hand side is a function of x of t and u of t, which is true because the first part of the left-hand side is a function of x of t, and the second part of the right-hand side is a function of u of t. Okay, this is just a mathematical convenience. And given we have written the differential equation in this format, Euler's method is actually given by x of t of 1, which is the system response at time instant 1, is given by the system response at time t0 plus delta t. Remember, delta t is the difference between the successive time instants. So again, Euler's method is the system response at time t1 is equal to the system response at time t0 plus delta t multiplied by the f of x of t0, time instant 0, and f of u of t0. That's Euler's method. Let's see how that actually works in practice for this differential equation. Okay, I'm going to apply this Euler's formula for time instant 1. X of t1 equals x of t0 plus delta t multiplied by f of x of t0. F of x of t0 is nothing but this part evaluated for time instant t0, which is nothing but minus x of t0 divided by tau, and this one is just the right hand side, the second part evaluated for time instant t0. So all we do is we just substitute t0 here, and we get the system response for time instant t1. You get the drift. For the system response at the time t2 is, we already know x of t1, we just substitute here, plus delta t multiplied by x of t1, we already know, we just substitute here, and u of t1 is already, it's known for all time. And if we evaluate the right hand side, we get the system response for the time instant t2. All right, let me illustrate this further. So at time instant t0, we know the system input stimulus, and we know the system response to be 0. So this is known at time instant t0. We want to find x1, which is x of t1, and it is given by x of t0 plus delta t, which is known, multiplied by, again, minus x of t0, which is known, tau is known, it's just a constant, plus k is also a constant, that's known, by tau, multiplied by u of t0. So if we evaluate this right hand side, we get the system response for x of t1, and again we go to time instant t1, and we evaluate the system response for at time instant t2 using this iterative formula. X of t2 is x of t1, which is already known here, and delta t minus x of t1, which is known, tau known, plus k by tau, a constant, multiplied by u of t1, which is known. So we keep on going through this iterative formula and keep on evaluating one step ahead at a time until all the elements in the time vector are exhausted, and at that time we are actually done with the numerical integration of this differential equation. Okay, all right, so the analytical part is actually done. We are coming down to the numerical solution, and we are setting, oh, by the way, the arrays in Matlab, they start at 1, not at 0. That's why the first element in the system response, I'm setting it to 0. What I'm actually saying is this here, the system, the yellow is the system response. The system response at the start of the simulation is actually 0. That's what I'm actually saying here. And u vector is, I'm creating a vector that is the size of the time vector. It is just a vector of ones whose size is the size of the time vector, and I'm actually multiplying this with k. Okay, so it's k in this case is actually 1, but it can be any value in for other differential equations. So we are creating the u vector, which is the system input stimulus. And delta t, we talked about it. It is the difference between the successive time instance, and we are taking the second element in the time vector and subtracting the first element in the time vector to get the delta t, this delta t here. All right, so this is all easy to understand. And the gist, the important, the main algorithm is actually in this for loop. This is where we actually implement Euler's method. Okay, the system response at index 2 is equal to the system response at index 2 minus 1, which is 1. We already know, set it to 0, plus delta t multiplied by the rest of this stuff is just implementing this equation here. Okay, so we talked about it. So we keep on going through the loop until all the elements in the time vector are exhausted. And at this point, we have the solution for the system response. And let me just put a breakpoint here. So this is the numerical solution. And in this part, we are comparing the analytical solution and the numerical solution. Let me just, and we find that the numerical solution is the same as the analytical solution. Okay, so this is how you solve a differential equation numerically in Matlab. And I hope you found this video useful. I will see you in the next video. Thank you.